So thank you very much for coming here and weathering all the storms, literally. So there'll be a few more that struggle in here, and then some that may even just wait till the networking. So if some of you haven't been here before, welcome to Purdue at Westgate's First Tuesday event. We try to design an opportunity every month to bring academia and government and small industry together so you can converse with each other, talk about new innovations, talk about what you could potentially add to each company. Tonight I'd like to introduce you to Charlie Kuznia. He's co-founder of Ultra Communications, which is a Samtec company, serving as president. His background is in the development of fiber optic communications for midboard and aerospace applications. He's previously served as Director of Photonic Products at pSemi and Professor of Electrical Engineering at the University of Southern California. So just for your information, if you don't know this, Samtec is headquartered in New Albany, Indiana, and I think he's going to provide some more information. But they are they have 40 plus global locations with over 14 global plants, I think it is. And I think they have probably 6,000 employees throughout the globe, I guess. Yep. But about 1,000 or more in the New Albany area. So it's a company that you would not know is there with as large of a presence that they do have. So Charlie will be speaking tonight on high-speed fiber optic comms for midboard aerospace. If you RSVP'd for this event, you will receive the slides, a copy of the slides in the recording. It's being recorded. So we'll send you that. If you didn't RSVP, let myself or Morgan Tavis know, and we'll be sure to get those to you. And I just realized I didn't introduce myself, did I? I'm Samantha Nelson, and I'm the program manager for here at Purdue at Westgate. I work for the Purdue Research Foundation, and Morgan Tavis is a marketing manager for us here too. So like I said, let us know if you did not RSVP and you want the slides and the recording, and we'll get it to you. So with no further ado, I'd like to introduce to you Charlie Kuznia.
Thank you. Thank you, Samantha. And again, thank you guys for and gals for weathering the weather and making it here today. So again, please let's make this interactive. If there's something you're curious about or a question or something I'm confusing you about, please just let me know. I'd like to make sure you all understand this. So the big picture here is Ultra Communications was a small business. We started in 2005 in San Diego and grew until a few years ago. We were acquired by Samtec. And Samtec is just down the road in New Albany. It's a really great experience. So, but our background in San Diego was making fiber optic links for satellites. And I was telling Stacy that our history was we were about to get laid off, and a satellite, the government needed a satellite link, and it needed to last for 20 years and high reliability, and somehow that landed in our lap in San Diego. It turns out we were making the circuitry that was rad hard. The technology we're using was known to be rad hard. We were doing it for the commercial industry, but the government realized that was rad hard. So they chose us, 4 guys, to make a fiber optic link for a satellite. We just laid off our whole staff, and the customer called and says, well, can you do this? And I think, well, I said, I think we could. Well, they said, well, this is a DX-rated contract. If you think you can do it, you're doing it. And it started our company. So we made a fiber optic link for space. But that's how we started. And so ever since then, we've been interested in space and high rel. We realized there's a market for high rel transceivers. So, but what I'm going to do today, I'm going to give you an overview of Samtec, and actually it starts out with a little video, and Samtec provided me these slides. These are very nice slides that I'll go. And again, any questions, please let me.
Welcome to Samtec. Today, we're proud to give you a glimpse into our world, one that revolves around you, and where our greatest strength is in connecting people. Connecting you quickly to the right solution, design tool, support person, or team to make your job easier. While you're here, we're excited to show you the latest technologies and give you a sneak peek into what we're working on for the future. But before we talk about where we're going, it's helpful to know where we've been. We were founded in 1976 by Sam Shine. At the time, he was working in marketing for a connector company and became increasingly frustrated with the lack of customer service anywhere in the industry. Sam set out to change all that. Samtec became the only company in the industry to offer customers free samples, extremely flexible product designs, and 3-day lead times. Today, we hold those same service offerings and many more that have evolved along with technology to make working with Samtec easy on our customers. If you want a single partner with products and support, from the bare die to the board, to a cable, to a panel, we've got you covered with the most advanced technology on the market. We know that our exceptional service, coupled with the most advanced technology, is what has enabled us to have more than 40 global locations and more than 6,000 employees. At Samtec, we're proud to still be privately owned and debt-free, with sales outpacing the industry year after year. Someone once referred to us as a different breed of cat, which is how our tiger mascot originated many years ago. Doing things differently is surely what has awarded us the ranking of #1 in the industry for customer satisfaction year after year. We take pride in making the most advanced technology products possible, whether it's cutting-edge medical equipment with the ability to save lives, energy-efficient products that make our living spaces more comfortable, or communications products that bring people together. Our customers and our employees inspire us to do better every day because of the impact we can make together.
So you can see Samtec is a big electronics industry in New Albany. And I worked with them, bought parts from them at when we spun out at Ultracom. Even before that, when I was a university, I was a grad student or professor, we would use Samtec. I never thought about it. But, you know, I always liked to work with Samtec. They always had a very nice, clear brochures, how they worked. They were very good. And also they gave you attention. You know, Samtec, now that I joined them, you can be from a university or a small business, and they'll treat you just like if you were Microsoft or a big company. And it's really embedded in their DNA is to work with everybody. And so, you know, I was groomed as part of the previous company. I was just like, ignore all those little accounts and focus on the big fish. You know, that's what we want to do. But they're very different way they work. And I think what happens is those little fish turn into big fish one day. They're hoping. Anyways, so as you know, if you know people looking, I mean, this is a really high tech, great company down in New Albany. So I just want to pitch kind of what's happening there. Let me go on. I'll show you kind of what they're into. So they have two kind of areas. Their bread and butter, and all up until I would say 2000s, was just board-to-board connectors. Just you'd think they're kind of boring. They're just things that snap boards together, and I think they're, you know, they sell them for pennies. You know, they're not much, but they're everywhere. They're in your cell phone, and they're all over the world. They're in computers, and they're just connectors. I say just connectors, but they're connectors. But in the last 20-some years, they've gone into more exciting things about silicon to silicon, and this is, you know, the chips that are going on your boards are getting massively powerful and needing to move a lot of data. And so they're creating much more higher speed board-to-board connectors. They have high-speed cables, RF cables. So if you need cables, that's a good, and they're very, I think they today have a tiny twin-X cable that's the highest density and highest performance that anybody makes. And then optics is why I'm here. But anyway, this is kind of their core business. So it's electronics, board, circuit board stuff. They are across the world. You know, they're headquartered here in I think New Albany's on there. There's New Albany. And the Optics group is out of Santa Clara, California. I'm in Vista, which is part of close to San Diego. And we also have a circuit design group in Phoenix. That's the Optics group. But anyways, Samtec as a whole is a very large company. Their business, as far as around the globe, they do have Chinese content today to be in that computer world, and to supply into them, it's required. 12% of their business ends up in the U.S., or where they make it, the manufacturing site is made in the U.S., but the bulk of it is in Costa Rica, Malaysia, and Vietnam. And this was all, you know, as they grew to make these kind of cost points, they went global. They're very wide. They really want to have a diverse customer base. If any of you ever got into a business and you found you had one big customer, you get beholden by that customer. Whatever that customer wants you to do, you're going to do, right? And so they've found a very healthy way to diversify across many areas: industrial, computers, datacom. And what I'm here to talk about mainly is aerospace defense, which is 11% of their business. Like I said, they're also in the consumer business. This is kind of the technical areas that you have to be in to serve this market, this silicon to silicon. I won't talk about this, but if you have any of these issues and you're facing in your design or in a box you're making, there's something called power integrity. Like the power supply can be noisy at these high speeds, or RF has to be quiet. So Samtec has a power integrity team. And if you decide to design something with Samtec product, that team will help you in simulation and work with you. And that's true for their microelectronics integration. They have lots of people on these. Thermal modeling, what happens to the heat. Samtec will help you with the thermal modeling. They do a lot of, as you imagine, precision molding for these connectors are all molded. I'll tell you a little bit about glass core technology. It's related to optics. As you go at higher speeds, these are things going a gigabit, 10 gigabit, 25 gigabit. We're getting 100 gigabit. It used to be it would be hard to find a 100 gig USB memory, right? 100 gig. Now every second we're moving that 100 gig. So it's amazing the data transport that we need to get to. But when you're moving that high speed data, there's issues of crosstalk, noise. So we have a group doing, all they do is signal integrity. This is in Samtec. So again, contact them if you're having these issues. We've gotten recently into additive manufacturing. The optics is what I'll tell you about. Material science, of course, a lot of these materials and things have a lot to do with how materials come together. I mentioned the high-speed cables. Also, I don't know if you saw in the video these machines that are doing, you know, this kind of thing, and there's machine vision. So again, if there's, you know, these are areas that Samtec specializes to do what they do. And I have another chart with what all these things are, but that's kind of what's happening here. So as I mentioned, this is the this right here is the old school stuff that, you know, for since 1976 when they were formed, was selling, and still today. The parts that are growing though in the last 20 years is this high-speed interconnect, optics, these cables. You can get cables that they connectorize them to be in very low-profile connectors that go inside of boards. And again, they're doing twin-ax and other really fancy stuff. The optics group and also RF. So these are kind of the businesses they are focused on. And then So this is a company started here in New Albany in 1976, barely a blip on the map, and they haven't done very many additions, but over the years now they've added our Ultracom Vista group in 2022, and they hit $1 billion in revenue. By the way, John Shine took it over from his father in 1995. So this is, you're trusting your son to take over the company here and wondering, will he be able to do what they've done in the past, right? Little do they know his son John Shine took it to here, right? So very brilliant man that runs his company. So any questions about that? I would really kind of get the word out if people are looking for, you know, a partner or work or whatever. It's a good outfit down there. So. Okay, so again, I'm looking for some interaction. So you know, let me know if you have something a question there. Related to this, so what's happening in the world, if you're not aware, the data rate that that's happening is in this orange line, and this is when products are released. So it was around 10 gigabits. We finally hit 10 gigabits around 2012. So again, 10 billion bits every second we need to move from these chips. And it wasn't very long, it went right to 25. And you know, and so today they're moving at 56 gig, 112 gig. So these, if you look at these massive chips, and it's driven by machine learning, AI, all these computing systems, they're getting massively powerful. And what this chart is showing is that Samtec's trying to be on the blue wave to get ahead of that, all right? Because they need to produce products that handle that.
So is that the data rate to a single cable?
That's a data rate in a port, in one port. And these will have multiple ports, these chips. So it's, if you look at FPGAs or NVIDIA ASICs, that's what's coming out of one port. Again, multiple ports. They're putting out terabits of data.
What's the theoretical limit that you can put through a single fiber optic cable?
There's a distance bandwidth link for multimode. So a multimode fiber is in this room could handle a terabit, no problem. But if it was going to go to you know, a city far away, I think it would probably be in the kilohertz. It drops off pretty fast. And single mode stuff, they're putting single mode goes city to city, a terabit easily per fiber today. And it's not limited by the fiber, it's limited by the technology that stuffs the light in the fiber and gets it out the other end.
Yeah, you hear a lot about the undersea. People don't realize that most of the internet traffic goes under the ocean in fiber optic cables, not through satellites.
Yeah, yeah, yeah. The link to a satellite's pretty slow. Yeah, yeah. But this is what one of these boards. I don't know if anybody's familiar with circuit boards, but in the middle here it might be a high performance chip that's just cranking out, you know, Facebook links and you know, Google searches, and what Samtec provides to that ASIC is how do we get the data out of it and move it to somewhere else. And so a lot of this is with these high-speed cables. They also have cables you don't see here that have even embedded filtering for supply. So these chips take amps and amps of current today, 100 amps into this circuit. Also, the fiber optic interconnects are coming out of these things. So they're putting fiber optics right up near this chip. The chip, why do we even put these interconnects so close? Why are we trying to get close to that chip? And the problem is the electrical signals, they don't drive very well across long boards, circuit boards. The circuit board, it drains the power out of the signal. circuit boards are made not in the best manufacturing for high speed. So there's an advantage to bring your interconnect. These cables are very nice 50 ohm perfect links, or the fiber optics are designed to move high speed data. And so these chips, if they only have to move a couple inches, it takes a lot less power to go that far, and there's a lot less loss. So this whole talk, I think I have embedded midboard is the word. All this stuff is called midboard because we're putting the electrical interconnects really close to those big processors. Okay, and so that's what Samtec, before they met me, they were getting into this business. And we were doing that for satellites for 20 years before that. We were putting fiber optics really close to processors. It turns out, you don't think of this, but the military in a lot of applications are the cutting edge. They're the ones putting these really high performance processors and image processors in place. And they drive us to put chips around the part. So anyways, that's kind of what I said. I think this similar pictures. You'll get these charts. They're really kind of, the graphics guys at Samtec are unbelievable how they, draw these things up. This is all make-believe, by the way. This is not anything real. But anyways, that's what they're trying to do. So that's a Samtec overview. I'm gonna leave before you, if you want to talk about any questions about Samtec. I'm going to go on from that.
Does Samtec make optics for the likes of like a Cisco and Aruba in the commercial space? Do they also?
Yeah, it's a big, just to put things in perspective, we ship about things maybe 10,000-ish a year into the military space, and they're shipping 300 to 500,000 into the commercial.
How effective were they by the COVID impact? I know that a lot of hardware was hard to get.
It was a disaster. So there was a certain chip that they needed for these commercial transceivers that they couldn't get. That nice man that drove the company, John Shine, the president, was flying around to these companies begging for ASICs, begging for them. It was so much so that even we knew people that worked in the factory that made the ASICs and asking them, do you have capacity? Are they telling us the truth? It was so desperate that you go to those kind of measures. And then you turn around and you're hurting your customers that need these parts. It was really difficult, and it lasted about 2 years. Then you know what happened? Boom, you got as many chips as you want, right? And you supply all those, and so people were over ordering if they needed. It was just like the toilet paper problem. They were over ordering, and so we were happy shipping. And actually, you saw that little blip. We hit $1 billion, and then we backed off. Well, that $1 billion was when we were shipping like crazy. And of course, now everybody has enough toilet paper, and they don't. And so 2023, this 2023 and 2024 are actually hard years for Samtec. Not difficult, but I think the number dropped off. You saw from $1 billion to 900, and I think it was like 800K or 800 million. Sorry, that it dropped off to. And so one of the good things is they did kind of project that this is probably overkill, and they didn't overgrow. So they didn't have to like right size the company. They were just sort of in this holding mode. And now there are signs that finally things are picking up again. So yeah, that was drama. That was for sure. Okay, so let me talk about now I'll get into the fiber optic stuff. There's one part about, so when we first met Samtec, it was really great connections because they were already doing mid-board fiber optics, and we were doing mid-board fiber optics, so we knew each other. They were trying to get into the aerospace business, and we already were in that space, so it was very good. But also they have a technology that's coming out of New Albany called glass core technology. Glass core technology. And so I have just a few slides about that in Samtec. It's a unique capability that they have. So the glass core technology is in, this is the, by the way, this is a picture of the Samtec facility here in New Albany. They also have wafer fab processes in Colorado Springs, and I'm not sure what that one is. That might be up in Wilsonville and Portland. But anyway, these are the kind of the areas where their fabs located. And what glass core technology is, it's taking a glass wafer. So it's, you know, the glass wafer, it's a clear piece of glass, and they're patenting metal on it. So this is like electrical interconnect. They'll patent it on there. They create what's called redistribution layers, which is really a fancy way of just saying it's a wiring pattern for chips or for interconnect. And then they know how to package these things up into packages that may be wire bonded or flip chip bonded anyway. So that's what's happening here. You can come up with a design and, you know, get, oh, I'm sorry, these are they make vias through the glass. I'm sorry, that was a picture of the first picture. So you can have glass on both sides of that wafer. You can have, I'm sorry, electrical connections on both sides of that wafer with vias that go through the glass. And that's a very unique thing. And then you can pattern on both sides of glass. I'm telling you this because this is used in our fiber optic packaging. So, but it's also, if any of your companies are out there looking for this, it's used for RF packaging and for high-speed ASIC packaging.
So what's the benefit of using glass?
That's a good question. So today that's available as on silicon wafers, right? You can pattern on silicon wafers metal. So a few of the things. One thing is a silicon wafer. Silicon, it turns out, is a semiconductor. You probably all heard that. And when you're running really fast signals on one signal, it turns out that wafer, because it semiconducts the signal to the next wire over. So there's a problem of interference. Glass is an insulator, so you get much better RF performance. For us, for optics, the glass is clear, so light goes through it too. So that's why you'll hear about it here.
How does it stand up to environmental aspects like vibration, shock, compared to something?
You know, it's interesting. There's a lot of types of glass today. We're working with Gorilla Glass and some of these that it used to be glass was a little bit more, I would say, fragile. But I would think it's right on par today as far as the robustness of anything you could use. So, with the and we do work in some of those Gorilla Glass things are developed for the cell phone industry. So in New Albany, you know, the types of things they have is they have a clean room. Again, this is just kind of what's going on in your state of Indiana. There's a clean room down there making these fabs. It's a full-on fab. They can do PVD, which is vapor deposition of materials onto a wafer. This is the machine that does the patterning. They're about I think there are 10 micron lines today. It's not cutting edge, but it's pretty dense. And then also you do a lot of polishing with mechanical polishing. So they have this equipment for that. I want to show you this slide because this is what what we do with it is so imagine this is a glass wafer. And you can make holes in it, and they metallize it, so they can do that. That's a through glass via. So you can interconnect metal on one side to metal on the other side. We can pattern metal, and here you can do a couple layers where you'll have a metal layer with a polyimide layer, then a metal layer. You can make bumps electrical contacts to it. You can put solder balls. And so this is a very useful for electronics packaging. Also, like we were talking about, this is like a 40 gigahertz band path with one of our customers are using this to make, you know, RF parts that were really good isolation. And these are just some pictures. This is, you're kind of looking at a piece of glass, and these are just the vias. And this shows some of the redistribution there. So anyway, this technology is available, and it's again, right here in New Albany. So I'm going to move on from glass processing. Any questions about glass? Yeah.
Are you doing any multi-die integration on those?
Yes. In fact, you'll see that in a moment. Yeah. Yep. So now let's talk about the group I'm from called Ultra Communications. So we were founded in 2005. We were 4 engineers. Again, we were about to be laid off from our company. It was getting out of fiber optics, and a surveillance satellite. It was a program came, and they needed a fiber optic link. These poor engineers making the satellite, they spent all this time making these cameras that each one of them was putting out 60 gigabits per second of data. And they had 3 of these cameras, so 180 gigabits per second of data was coming out of these cameras. And imagine these cameras are looking at Earth, very high resolution, very high frame rate. It's for, you know, these surveillance satellites are watching for troop movements and all kinds of signatures and things on Earth. And they spent many years developing the camera. On the other end, they spent a lot of time, how do we deal with the data processing, because you can't put all that data down to Earth, so there's a computing system. And then they got the satellite chassis, and they realized the chassis was only 3 inches in diameter, and you could not fit 180 gigabits of data down that chassis. You couldn't fit it inside the tube. And so they were forced to use fiber optics. That was the only way to move that much data. They had to move it 5 meters, and at that time, this was in 2005, the technology, the only thing they could do was fiber optics. So that's how we were started. It was a desperate situation for the government. But anyways, we grew to be 54 people. We're 16,000 square feet. We have our own clean room. Again, our background is circuit design. We came out of a circuit design group. We do fiber optic package, and we started manufacturing our own parts in 2017. In 2017, we supplied to Lockheed, Northrop, BAE, all these customers were buying our parts, and we could ship about 5 each. And then they came back and they said, well, we need hundreds and thousands for our programs. And so then we got ourselves into trouble. That was a whole nother story. What we do, if you look at a fiber optic component, if anybody's ever seen one of these, it's they're designed in these big packages, these big metal packages, and they're designed to be in an air-conditioned room, in a data center that's air-conditioned. Everything's nicely controlled. Not mid-board. They're designed to be out in a nice, cool environment. What we do is make the parts, we shrink them down to tiny parts. We design them to be to survive in harsh environments, extended temperatures, radiation, all this. Today, these parts run from 10 megabits per second to, we have customers that want to run very slow over fiber optics, and then also want to run very fast. The products we have multiple fibers, so they'll have up to 12 fibers typically that'll be interconnected to this part. And again, what this part does, I'll pass one around. What this does is the high-speed electrical signals come to it or from it, and it just converts it into optical, puts it on the fiber, and puts it on the fiber. On the other end, it takes them off the fiber, puts out electrical. So that's all it is, a conversion. Like I said, but what we did from day one, since our day, this was our business with satellites, was designed to be these really harsh environments with thermal cycles, small packaging to package it near the big processor, and get it onto, now today we're on satellites and airplanes and other things like that. So I'll send this around. This is what our transceiver looks like, and this is the fiber cable. Make sure you look at both sides of it. One side has, you can see these little square dots, those are ASICs. You're talking about multi ASICs on a, this is put onto, actually it's sapphire, but it could be put on, we're putting on glass too. That's made this part. And on the top, there's a features that this fiber connector mount to, and that these things come together. So this is how the light comes to the part, leaves the part, and this is what's soldered to the circuit board. So, anyways, show and tell. So where this harsh environment things, it turns out automotive, although we're not selling in this today, that we had a lot of companies coming to us, but we're making parts for satellites. We're not the right price point for automotive, but there is fiber optics going into cars. Obviously, Aerospace. We are talking to quite a bit on the cell phone base stations to make a fiber optic link from up to the antenna down to this. And these are not very well controlled environments. Shipboard also. These are kind of the key markets that we're looking at. What do you need fiber optics for, and what are they used for? The typical thing is there'll be a sensor like a camera. And you imagine your cell phone has these very high density pictures, a lot of data behind them. There's also radar systems. Sometimes they're just moving data, so data from one place to another. So there'll be some kind of sensor, imagine a camera, and it outputs this data on a fiber. And then it goes to maybe some computing system. And that computing system's also talking to storage, so like a memory system. So all this fiber optics is moving this data. Today on the F-35, the pilot has a heads-up display, and what he's looking at on his display is delivered to his helmet with fiber. And it goes from a computer system that takes all these sensors and all the data, looking around the scene up and down through his legs, and projecting that on his screen. All that's done with fiber optics. So this is where it's kind of used, but it's widely used throughout the DoD. This is just, you saw already the chart of how fast data is going up, and it's because technology is getting better and better. We started off a while ago. We were all happy with our full HD high definition televisions, and well, then it goes to 4K, 5K, 8K, geez, and now the 10K. And by the way, this home use is 8K. The use in DoD on these resolutions up to this would be a standard frame rate. This only took 9 gigabits per second to transmit that uncompressed image, but now we're at 190 gig. Just all of a sudden, because our cameras got better resolution and better rates. So this is just what's happening. Again, it's just what's happened in technology over the last 10, 15 years. It just really exploded what they can do with and what they need to move. The market, so there is a forecast for harsh environment fiber optics. It's a thing now. It's about $1.5 billion in optics. The transceiver portion of that is I'm sorry, that the transceiver portion is, well, I guess it's a little higher now, $2 $2.5 billion market for what we're talking about here, transmitters and receivers in this market. The majority of them are not on the airplanes and things. The majority are ground-based parts. And like I said, we've been into satellites. Well, there's a missile warning systems that go on tanks that use fiber optics to look out at the field. They're very high resolution warning systems. F-35 I talked about. The next Patriot missile system has fiber optics. We're going into general computing boxes. Also particle accelerators that need rad-hard mid-board transceivers. So this is kind of the market for all you business-minded people out there. Okay. It's a great market, great technology. There's a need for it. So what are the challenges to making a fiber optic part work? So first of all, you're using commercial things. We're not inventing lasers. We're trying to take what's available commercially, maybe make a better ASIC that runs it faster, but we're trying to take what we can get from the commercial world. You know, these aerospace systems, they want minus 40 to 85 typically. Our current part wants to go up to 95 C. The components you get, any laser you get is susceptible to temperature. When the temperature changes, the wavelength of the laser changes, which you might not think is a big deal. But some systems, they use like wavelength multiplexing. It turns out you can't use that on an airplane because the temperature, without some drastic cooling measures or something. Also, even you have a problem that you have if you have anything in your system that's sensitive to wavelength, like a filter that you're trying to filter out light, and all of a sudden your wavelength changes, you have a problem there because your filter's not designed for that. So that makes it hard. Also, if you look at what's happened over the last 20 years, it used to be the commercial supplier that supplies hundreds of millions of lasers, hundreds of millions of them. They used to spec them from, at the beginning, minus 20 maybe to 70 or 85. And then all of a sudden, they get to 10 gigabits and they only spec them from 0 to 70, right? And now you get to 25 gig and they're saying, well, maybe 20 to 70, right? So they're as the data rates increase and they're pressing these components harder to move data faster, the commercial world is limiting their temperature range. But it turns out the airplane and the satellite, they didn't change. They still need that wide temperature range. So that makes it harder for us. Some of the systems you talk about that they use active cooling, like a thermoelectric cooler. But as soon as you do that, you all of a sudden you need thermal control circuitry. It takes 10 times the power, and again, it's not really feasible. So these are the kind of things that we have. Also reliability concerns that we have to deal with. The other thing is the package that you have. It has to survive 1,000 thermal cycles. They don't do this with commercial parts. Minus 55 to 125. It's got to survive. Shock and vibration. This is a spec we recently got that wants 1,500 kilog's of shock. Our previous customer wanted 100. So we don't know is the answer. We need to go out and do that. But apparently during the launch, there's some significant significant shocks that can occur during a satellite launch. Also for the airframe guys, there's shock of the airplane landing, especially on a carrier deck. It's a hard landing, and it can even amplify as it goes out onto the wings where some of this equipment is. Also, there's the commercial guys, they don't have to worry about moisture. They're in an air-conditioned room. It turns out when we first found out where we sit in one of the airplanes, they have weep holes on the box and that's it's going to get full of moisture, salt, things, and it's going to leak out. So your part has to survive with salt spray and all of this. So optical elements, lenses don't work if they're full of water. Just like my windshield didn't work when it was full of rain today. The electronic components, that wiring I was talking about, if that's exposed, that could be a problem. And then lastly, we have radiation, so space. So I think we're all speaking to the same choir. We're at the Navy here. You know about these nasty things you do to parts. Like I told you, the reason they came to us was we had a boom. They had to move 160, 180 gigabits down. And so, but if you just look at, if you try to just move 40 gigabits, not even 180, just 40 gigabits over 10 meters. And I got my cable that's rated for that kind of environment. It would take me 20 cables to go 10 meters and 9 dB loss. So it's an inch and a half diameter of a cable bundle. And it would weigh 7 pounds of weight. If I do the same thing in which we did over fiber, we had at that time just at 2 gigabits, 20 fibers, which 0.2 inch diameter, very flexible, 0.4 pounds. So you putting something up into space, weight matters. You put things into an airplane, weight matters. And this is really what's driving fiber optics. I used to need this slide because I was sitting in a room of people saying, why use copper today? Tell me why I would want to use fiber. And so I had to make this argument. But it turns out nobody asks us anymore. All our customers are already going, how do I get fiber onto the airplane? The other thing is once they have the cable plant in place with fiber, they can easily upgrade it from 1 gig to 10 gig to 25 gig to 50 gig without changing. I don't have to change my wiring, so that's another bonus. Okay, so this is all the motivation, all the trouble, what you have to do to get into this space. And so I'm going to talk next about fiber optic transceivers, what we're doing. So you're all convinced this is difficult and it's needed, right? So this is what I just went around the room is what we developed at Ultra Communications about 8 or 10 years ago. It's called chip scale packaging. So chip scale packaging is when it used to be you've had a chip, you'd put it into another package and wire bond it, and then that package would then be soldered to the board. Chip scale is when you have the element itself and you put solder balls on it and you mount that onto a board. No outside packaging. And that's how we get it so small. So you saw the commercial things were in these big metal frames. Most of that is because there was big electrical connector at the back, and there's a big optical connector on the front, and I need the mechanical support of that. But when you start getting rid of things and you put the fiber connector on the top, you don't need so many parts anymore. So we made a very simple transceiver. And what we started with is this, it's like glass core technology. If we didn't know about glass core technology, we were using another company back in the day that would make a wafer and they would metalize one side of it, put electrical routing. So imagine this is a glass or sapphire, we call it a carrier substrate, there's metallization on the bottom of it. Metal's like little wires running around. And what we do is we take our transceiver ASIC, so it's a silicon ASIC that came out of Tower Jazz, commercial ASIC. We diced it down and we put little solder bumps on it, and we solder it to that carrier. And the carrier has wiring to interconnect that ASIC. And we do the same thing. There's The lasers today come, these, I didn't show anything, but they're called VCSEL devices. And if you can imagine this, it's a millimeter long, this chip, 1 millimeter. It's 250 microns wide. And you just saw it. It was on the back of the chip that you barely saw it. So, but you know, when they fall on they're like pepper flakes. They're hard to find. But we flip chip that, and the 4 lasers are pointed upward, and the light goes up through this carrier. And the same with the photodetector array. We flip chip that, so 4 detectors. And the reason I'm saying 4 and 4 is I have 4 different light sources that are going into 4 fibers. And I have 4 fibers that are sending 4 signals down. This is our standard configuration. We call it 4 plus 4. But when we flip chip these things to the bottom, we flip chip a microcontroller. A microcontroller is important for, as I mentioned, these lasers change behavior over temperature. So we have to calibrate these lasers to work over this temperature. And so this is all done. This is an electronic assembly of multi-chip module and multi-chips onto this carrier, all interconnected. So the ASIC's attached to the lasers and the detectors. The microcontrollers talking to the ASIC. And also there's around the perimeter, these kind of blue dots there are solder balls. So this part can be just soldered down to the circuit board. Nothing else. And then on the top side, we have this light coming out of the laser. The light leaves this little chip, this tiny chip I told you about. The laser is about 10 microns in diameter. And the laser is coming up as a cone of light. It's diverging. And so we use a lens that collimates this beam into a beam. And that goes up into our fiber connector that has another lens that focuses it into the fiber. So this sort of setup, like I said, we developed this, and by the way, we were doing, once we landed our government satellite program, that was beautiful, and it was really great feeling that we shipped the parts to the customer and ended that contract. It was a DX rated contract important to the United States. But the day after that contract ended, we had nothing going on, right? That was great. We finished it, but now what do we do next? And so our little company got into, we were a small business, so got into many SBIRs. And so all this was developed under SBIR programs. And you can see success stories out there and stuff we've written. But this Fiber Connect was made, all this system here was made under SBIRs, and it's been now a workhorse for 10 years into product, so it's been great. Today there's the speed of the device. So we talked about 1 gig and 10 gig and 25 gig. The speed of the device, how fast we can turn those lasers on and off. So 10 gig is 10 billion times every second. 25 gig is 25 billion every second. We need to turn that little laser on and off. And so that's done by this ASIC right here. And we have 2 versions of the ASIC. One's called Malbec. And later I'll tell you about the space heritage of Malbec. That's the one that's flying in space today. And we have an upcoming one that's Winslow that goes to up to 32 gig. And so that's what defines, obviously you have to have the lasers that run that fast in the ASIC. So any questions on that? Okay. This is kind of a blown up picture of what you were looking at. So this is the bottom side. The part that you sent around there, it was all white because it was, they did like an overfill of epoxy. This is a part without overfill. But this is the transceiver ASIC that drives four VCSELs and receives from 4 pins. So this is the VCSEL array and the pin array. This is the microcontroller, and this is, you see all this kind of, that's it. It's actually, I think, a copper routing that interconnect everything. You can see the high-speed signals come in from this side, and then the microcontroller is routed through some signals here to this, and the microcontroller goes out to the world. And then these are the ball grid arrays. This is a perimeter balls that solders to the circuit board. So that's what it looks like on the bottom side. So you can see this flip chip assembly you were talking about. And it's all done with flip chip bonders. The ASICs are done with 0.3 micron accuracy. So we don't have to actively align anything. It's all done, the lasers and the lenses. And this is what it looks like on the top side. So after the assembly, we put this lens system on, and it has these 4 slots that the fiber connector goes into. So this part is the workhorse and the reason that Samtec acquired us. Because this part, we were running at 10 gig, 25 gig. We simulated it could run at 50 gig higher because there's no extra wire bonds or a lot of electrical circuits. You could run it very fast. And where Samtec was going was to going to something like this inside their 50 gig and 100 gig per channel modules. So this is the technology we developed. This is kind of a cartoon of how this thing mounts on the top. So I think you get that. So what does this do for you? Okay, so one thing is the VCSELs are the most reliability concern, the lasers, it turns out. So you want to keep them as cool as possible. If I put everything on this side, my ASIC's drawing a couple watts of power. If I put all this down on the circuit board, the space guys, they have heat sinks in their circuit board. They're pulling the heat out the bottom, conduction cooled. So you have a very good thermal path to the circuit board, which is different than the commercial parts. The commercial parts are trying to get air cool or some other type of cooling. So the solder reflow, you can solder reflow this part to the circuit board, get a very intimate thermal interface, and then you can plug on the fiber connector later. So you send your parts through the solder reflow to your board, and then you can put the connector on later. Also, by getting rid of all that extra stuff, we have something that's very small, as you saw. Very light, 0.4 grams, 1.5 watts of power. And we can make it work over this wide temperature range. So everything you saw also in there, all those glass components in the transceiver part of it, were all with parts between 5 to 7 parts per million degrees C, all thermally matched. So this means over thermal cycles, I'm not having stress. The fiber connector you saw was plastic, but that plastic, we designed those slots that the plastic would just expand and contract down the slots, no stress. So we designed this thing to stay optically coupling over this wide temperature. And this is why we're very different than anything you'd see designed for commercial world. Commercial world, if it adds a penny, I don't want it. In our world, we optimized for performance, not for cost. So again, the fiber cabling comes in after the part's soldered down. We, just because we're not connector guys, we have a strap with 2 screws. It's simple, screws that to the board. Also, a lot of our customers will use 3 of these, and they'll bring the fibers together into 1 cable. So it's called we call it a trident. But this is typical use case of our transceiver. They'll have 3 of them, and they'll bring them together into 1 fiber. So that's what Ultracom brought to the table in this thing. So does everybody get what I'm trying to do and trying to say? Okay. There's a Firefly platform that existed at Samtec as we came in, and it's very similar to ours, except it's similar that it's in the mid board. It's right near they want to park these by these big processors. But they came at a different approach. What they do, they put an electrical connector on the board first, solder that on the board. And once you've soldered your whole board, I have a module that's pigtailed with the fiber. So they're connected. So it's like a dog with a tail. And I connect that part onto the circuit board. I don't solder it down. I put it into the connector. Okay? And that connector handles up to about 32 gig per fiber. And today, Samtec is selling, and these are like 400 million of those. And then as I go up in temperature, it goes down by about a factor of 10. But this is huge commercial applications for AI computing, for for the big simulators, Siemens, for Cadence. Today you tape out, if you're familiar with the circuit design process, you design these incredibly complex ASICs that take years to design, very complex simulation of these ASICs. And so the circuit designers using these simulation tools provided by they're called EDA, the electronic design automation tools. And so you sign up with Cadence and you send your circuit design, you're working with Cadence, they have the computing system at their site. You don't even compute it at your local one because the complexity is too hard. And you work on this, and those big computers they're using these fiber optics because of the complexity of the computing. It's different than like a data center computer. It's this very high performance computer. And once you tape you finish your circuit design, you've simulated it on in their computer, your chip, it lives now in a computer. And they tape these things out, and the people, they continue to work with that chip. They start developing firmware, just like it was real. They develop all the firmware. So everything else that it takes to make a chip, they even put packaging around it and simulate it with a package. So when the actual hardware comes out, you've done exhaustive simulation of that ASIC, and it's ready for market. Because that timing to design is a long, and then the fab process and the packaging process, the test process, all those can be 2 years long. And if you screw up at the end, that you just may have lost the business, right? So these Fireflies are the horsepower behind that simulation tools in the commercial. That's why they're selling so many of those. But they also have one that goes wider temperature. Now they're making them, they're sealed so they can be in harsh environments. And so they're also going, they were going that route independently of us, and now we're together selling into these markets. They also have something called that uses PCIe. If anybody's interested in that, we can talk about that. Okay, so this goes up to 32 gig. What do we want to do when we get past 32? What's the platform? So this is where this CSP comes in. This is what we're doing with our platform of flip chipping. That's now going into a module. But this is what it looks like. The module's up underneath here. If this part is actually in here but flipped down. But this is the optics. There's a fiber connector that goes to it. But the center of this is the same structure, the same flip chipping of VCSELs and pin detectors and ASICs onto a glass carrier. And the glass carrier is now made by GCT, which is owned by Samtec. And all of that is vertically integrated. They can make this transceiver. And so this transceiver now is designed to go above 32 gig. There's a whole bunch of features in it that make it easier to use, to snap in for the customer. But anyways, the goal is to get up to 112. That's what's in development right now, is 112 gig and optically pluggable. So if you're concerned after I was talking to you that, oh, well, Charlie, I need more than 32 gig. Well, we have more than 32 gig. And here's a roadmap. By the way, this is just about a month ago, we got the 56 gig to work. So there's our happy engineers finally turned this part on. But, the Department of Defense, so why is it so important that we have GCT inside? Why is that a big deal? Maybe, reduce costs, or we have vertically integrated. What does that do for us? It turns out having our own ASIC, we designed our own ASIC for 10 gig. Having that available for the DoD, these programs go for 20, 30 years, right? And having that ASIC available, it's not an obsolescence problem where it doesn't exist anymore. This is the roadmap I just talked to you about, which we have this, they call the CSP now, it's called the Firehawk, and we have a 10 gig version. We're gonna have a 32 gig version, and then this Halo is taking off, and this is our 56 gig early results. It's still not cleaned up, but it's working. Okay, so that's everything about transceivers. I just have a very brief part to talk about what's happening in space. I don't know if is there anybody from the radiation side of things here in this meeting? Okay.
We have a little time.
Okay, little time.
They leave at 6. The food and drink leaves at 6.
Okay.
So.
Oh my, I don't want to be between that. So
I want more conversations to happen after that.
actually, you'll get these slides in the back, and so I'll just do a summary here. So because we were circuit designers, we designed to handle radiation. So the circuit itself was designed to work in these space. Like I said, we've got space heritage that we've actually, that satellite program came to us the first time we delivered. They came back again, and we went from 2 gig to 3 gig. But we also have ongoing satellite sales. So this is kind of our business for us is space, number one. We have 2 transceivers today for satellites, is this 10 gig version and the 25 gig version. So if you're interested, what does that mean to you? So 10 gig is 10 gig per fiber, and one part could do 40 gig out, 40 gig in. And then there's a 25 gig, so it can do 100 gig out, 100 gig in for this system. And also, a lot of you, maybe you're wondering how slow can it go? We have down to 10 megabits per second. So these are available. We've had 3 space customers do significant testing of these parts, including heavy ion, total dose, heavy ion and proton source, neutron source, and also ELDERS, which is low rate. ELDERS is low rate radiation sensitivity. We've done that. And this will be my last slide. This is a summary. So if you want to know, like, hey, what is my system? This is what we've done. I think we haven't done, you might be interested in like a flash situation. We haven't done that. But this is basically the space requirements for geo operation. So we have quite a bit of data on that. So I think the big numbers are, it doesn't, the circuit, if it latches up, it destroys itself. So we've never seen that happen up to 77 MeV. The registers that control the lasers, there's no resets below 46 that we've seen before, 46 MeVs. Also no damage at 85 to anything. And anyway, you maybe know these specs better than I do. So. And that's it. So any other questions that I missed or curiosity before? Who dares to ask a question between us and food?
I'd just like to say something real quick. So I'd like to thank Charlie for coming all the way from San Diego.
Yeah.
I'm the Senior Vice President at ARI, for the Silicon's Crossroad Hub, which is one of the 8 CHIPS-funded hubs. And Ultratech and Samtec are a member of our hub, a very active member. They've done some really great work with us, and we're real optimistic on some future teaming. But as you see this technology, if there are ideas going forward, particularly for real project applications, because the 2 main purposes of doing this with the CHIPS program is to address the domestic supply chain, which we mentioned, and we talked about that. We don't want to be dependent on having to go out and beg for chips in the future. We want to be able to have sources that last the life cycle of DoD programs, and then advance the transition, speed up the transition into new DoD platforms. Thanks.
Thank you. Okay. All right.
Yeah, let's give an applause to Charlie. He did come from all the way from San Diego, so I appreciate him coming in. Brett was instrumental in getting us here and helping me understand how important it is of the work that they do. So I appreciate him coming. I appreciate you all here. This is something we do every first Tuesday if you haven't been here. So next first Tuesday will be May 7th. And going to do a little bit of a twist. We're going to have Mitch Frazier, who is the Chief Executive Officer of AgriNovus. If you don't know who AgriNovus is, they are a nonprofit organization that looks into ag bioscience. So they're going to be talking about ag bioscience and the cornerstone of national security. So they're going to be talking about the food industry and how it affects national security. So very interesting, a little bit of a turn for us, but very important, especially in the southern region when we have Knox County and a lot of agricultural areas. So we do have food and drinks outside too, so please continue the conversations. I didn't mean to stop the presentation, but a lot of good comes out of the conversations, and a lot of relationships come out of the conversations that happen during the networking. So again, thank you for coming, and hope to see you next time. Thank you, Charlie.